Hi, let's continue our discussion of control systems by looking at the effect that the location of a pole has on the transient response of a particular system. Now, we've already looked at the partial fraction expansion, right? We did a partial fraction expansion when we were looking at the output of a second order system. And you can see that if you do a partial fraction expansion of a general transfer function and you write out the time response, you have a variety of exponential um, decaying exponential signals. And you can see that the pole location actually determines how fast the signal is going to decay. So if your pole is very close to zero, it's going to decay much more slowly. Am I right, or is it the opposite? Okay, yeah. So if you have a signal that is very close to zero, then you don't have any decay. You just have a constant signal. But if you have a pole that is much further away, then it decays very fast. Okay, and that's one of the reasons why you could ignore the pole in the previous video. If you remember, you have an extra pole, and if the pole is very far away, you can ignore it because the response due to that pole decays very quickly. So let's look at how what is the effect of pole location on the transient response. So if your pole is, let's just look at the response on the real axis. If your poles are on the real axis, then as you move further away to the right, to the left, what happens is that your your decay becomes faster and faster, right? If you go towards the right, that is towards the positive real axis, your system actually, instead of the response starting to decay, it starts to increase, and you have what is called instability in the system. We'll talk about unstable systems in the next lecture. Now, if your system has complex poles, then you have oscillations in your system. You have the sine part of the signal. But the amplitude of the sine wave still continues to decay in much the same way here. So if your real part is towards the left, you have a faster decay of your sine wave and you start reaching your steady state much more quickly. Uh, and if you go on the right hand side, instead of decaying, your signal actually starts to increase and you have unstable systems. So at zero, at the on the imaginary axis, you have systems that just don't decay, right? They're still, they are not really unstable because the input does not increase with time, but neither uh, are they stable because the response doesn't decay with time. It just stays the same. So we call such systems marginally stable systems.